In the NCEES Fundamentals of Engineering exam, knowing the material only gets you halfway to a passing grade. The clock is a constant threat, and finding the right numbers quickly is just as critical as knowing how to use them. Your only permitted resource during those 6 hours is the NCEES Reference Handbook. This is the Fundamental Constants page. Without a search strategy, it presents as a dense wall of raw data. Students consistently miss thermodynamics and chemistry questions not because they misunderstand the science, but because they misinterpret the specific nomenclature baked into this exact table. Grabbing a constant with the wrong unit base triggers a cascading calculation error. The test makers know exactly which errors are most common, and they design the multiple choice distractors to match those incorrect results perfectly. Memorizing formulas won't protect you here. You have to master the visual layout of this specific handbook and anticipate the unit traps embedded inside it. Look at the introductory paragraph positioned directly above the constants table. The manual designates this symbol, R bar, with a very precise definition. R bar is the universal gas constant. It applies to all ideal gases equally, regardless of their chemical makeup. The text provides the mechanical relationship. When you divide that universal constant, R bar, by the molecular weight of a gas, you get the specific gas constant, designated by a standard R. That standard R is unique. Its value shifts based on the molecular weight of the exact gas you are analyzing in your problem. The NCEES handbook includes a direct warning at the end of this paragraph for engineering disciplines. Chemical engineers often use an unbarred R to represent the universal gas constant. On the FE exam, falling back on that discipline-specific habit is dangerous. If you apply the chemical engineering convention and plug a universal value into an NCEES equation that requires a specific gas constant, your calculated mass will be entirely wrong. Assuming an R value of 8.314 without visually verifying the bar notation above it is a fast track to dropping guaranteed points. Moving down from the text, we get into the numerical data of the fundamental constants table. There are 4 rows dedicated to the values for the universal gas constant, R bar. 2 of these are metric, 8,314 joules and 8.314 kilopascal cubic meters. The numerical values scale directly with the chosen units. This redundancy allows for dimensional alignment. If your problem provides a volume in cubic meters, selecting the kilopascal cubic meter constant immediately pre-cancels your variables, saving you a conversion step. However, both metric constants hide a trap in their denominators, the kilomole. Introductory chemistry classes drill the standard mole into students' heads, making the unprefixed mole the default assumption for most test takers. If you calculate standard moles and multiply them by these NCEES metric constants without converting to kilomoles first, your final answer will be off by exactly a factor of 1,000. For problems in the imperial system, the USCS value of R bar jumps to 1545 foot-pounds force per pound mole Rankine. Choosing a constant from this list requires a strategic look at your specific units. You have to align the base dimensions perfectly before you ever start pushing buttons on your calculator. Looking at the entire block of fundamental constants shows exactly how much data is packed into a single page. To find variables quickly during the exam, you need to partition this list into distinct engineering disciplines. For chemistry and circuits, the top section holds the electrochemical values, specifically the electron charge and the Faraday constant. Grouped further down are the mechanics and fluids variables, Newtonian gravitation and standard gravity acceleration. And rounding out the list are the physics and heat transfer constants, providing the speed of light and the Stefan-Boltzmann constant. Looking closer at the standard gravity acceleration entries reveals another precision test. The handbook provides the USCS value of g to 3 decimal places, 32.174 feet per second squared. Most academic programs teach a rounded 32.2. Using that rounded 32.2 from memory instead of the exact 32.174 creates slight calculation variations. Those variations often lead directly to the exam's incorrect distractor answers. The table also includes one final, highly specific tool, the molar volume of an ideal gas, V sub m. At standard temperature and pressure, 1 kilomole of ideal gas occupies 22,414 liters. Knowing this value is listed here lets you bypass the entire ideal gas law equation for STP problems, saving several minutes of algebraic work. Treating this table as a toolkit stops you from scanning randomly. It literally buys you time, when every second counts. The FE exam throws a massive volume of information at you, and the manual is dense by design. Safely navigating the constants table requires following 3 absolute rules. First, look for the bar. You must explicitly verify whether the equation on your scratchpad demands the universal R bar or the specific unbarred R. Second, match the unit base. Choose the constant version that pre-cancels the specific volume, pressure, or energy variables given in your problem prompt. Third, check the molar prefix. If you select a metric constant with a kilomole in the denominator, you must convert your standard moles to avoid an off by 1,000 error. Walking into the testing center with a systematic approach to the reference manual prevents the frantic, time-killing keyword searches that derail so many students. Passing the FE requires proving you are fluent in the exact language and layout of the NCEES reference handbook. By mastering the specific nomenclature and spatial organization of this data, you turn what could be a trap-filled minefield into a reliable engine for rapid, guaranteed points.
Welcome! In this video, we will learn the ideal gas law, the key constants behind it, and solve problems step by step. The ideal gas law connects pressure, volume, and temperature. The equation is PV equals nRT. Let's visualize a gas in a container to make it more intuitive. The ideal gas law uses important constants. Let's list the 3 most common ones. R is the ideal gas constant. K sub B is the Boltzmann constant. N sub A is Avogadro's number. Example 1. We use PV equals nRT. We are given N equals 2 moles, V equals 5 liters, and T equals 300 Kelvin. We will solve for pressure. First, write the equation. Next, solve for P. Now substitute the values. Finally, compute the result. Example 2 uses the microscopic form. PV equals NK sub BT. We are given N equals 3 times 10 to the 24th molecules, T equals 350 Kelvin, and V equals 0.1 cubic meters. We solve for pressure. Write the equation. Solve for P. Substitute values. Compute step by step. Final answer. Now it's your turn. Try this problem. 1 mole of an ideal gas is at 273 Kelvin, and the volume is 22.4 liters. Find the pressure using PV equals nRT. Pause the video and work it out. Now let's check the answer. Let's recap the key idea. The ideal gas law connects pressure, volume, temperature, and amount of gas. Choose the right constant, plug in the values, and solve step by step. That's it.